Lots of times when I talk about vectors, they're free vectors. They just tell you you have a starting point, you have a horizontal component and a vertical component, and you start anywhere. A position vector is called a fixed vector because its starting point is always the origin. And so anytime we have any point anywhere, we can have a position vector. And I can add an arrowhead over that. So the vector P starts at the origin, goes to any point, and we can do this in 2 dimensions or 3 dimensions. So we're going to sketch the position vector passing through -6, 5. So you just find your regular coordinate, -6, 5. Go from the origin to that point. And we could write this as a column vector or with the i's and the j's. I underlined them that time. I like the arrowheads over top.
I had J hat.
Hats would be the unit vectors, which they are unit vectors as well, because I is just 1, 0, and j is just 0, 1. So technically would be right, but we just put arrowheads over it. And now we can get close to doing math with vectors. So far we've been doing a bunch of setup stuff. So if we consider the points A, 1, 3, and B, 4, 5, we could draw their position vectors. A and B. So my position vector for A is the blue one. My position vector for B is the green one. And here's the first sort of big idea with vectors. If you're at point A and you want to get to point B, you can always take the long route of going back to the origin and then from the origin going to B. It's not efficient, of course, but we're not worried about efficiency with vectors. In vectors saying if you wanted to get from A to B, you could go from A back to O and then go from O to B. And this is it has something sort of similar to matrix multiplication. So here is the equation that I just said. A to B is like going from A to O and then O to B. And do you notice, just like in matrices, we had things that were compatible with adding vectors? If those middle numbers or those middle points are the same, they're both at the origin, this is just like going from A to B. Just a longer route. But in vectors, the distance that the route takes doesn't matter. As long as you have a starting point and you have an ending point, it gets you to the right place. And since A to O is the negative of OA, right? Because OA is going in this direction, A to O would be its negative. We can always, and I'm going to write it here again. We can always get from A to B by going negative O to A plus O to B. And sometimes we will denote these vectors as this is vector A and this is vector B. So A to B is negative A plus B. And you'll often see it written as B minus A because it's easier to subtract than put a negative out in front and add. However, for your mental thinking, negative A plus B will make more sense. If I'm at A and I want to get to B, it makes sense that if I'm only allowed to follow along the blue and the green pathways, that I would go negative along the blue pathway and then positive along the green pathway. It's much less visually easy to see B minus A, but I'll show you what B minus A means. Here's B, I'll draw over top of it. If I do B first, that means I'm starting at A and I would go up over there. That would be doing B first. And then negative A, which is this arrow, gets added on after. Do you see that doing B minus A gets you to the same spot in the end? But visually, that's hard to see in your head. It's much easier to see, okay, I can go back to the origin, negative A, and then add B. That's my resultant. This isn't a huge idea, but picturing this is going to help you a lot moving forward. So this is a key idea for understanding that if you want to go from any point to any other point, and this is true in 2 dimensions, in 3 dimensions, if we wanted to in 4 or 5 dimensions, you can go backwards to the origin and then from the origin go to the other point. So you can use your position vectors to solve this. Right. So here we are in 3 dimensions, -2, 7, 5, and 4, -3, 2. I'm going to attempt to draw this in 3 dimensions to show you what you're trying to find. You are trying to find, so here on the table, got my X and my Y axis, and then my Z axis going there. Point A, I'll do all of my work in point A in blue. So -2 in the X direction, 7 in the Y direction. And then 5 up. Oh my goodness, there we go. There is the point A in 3-dimensional space. I went 5 units up. So -2 in the X direction, 7 in the Y direction would get us the point -2, 7 in our XY plane. And then we had to go from that point 5 units up. So there's the point A in 3 dimensions. The point B, which I'll do in green. 1, 2, 3, 4. -1, 2, 3. There it is in the XY, and then 2 units up. Measure that. About there. And we want to find the vector A to B and B to A. So here is what, you're somewhere in 3 dimensions, and you want to go from there to there. It's a little bit bent, isn't it?
Yeah.
That's okay. How do you do that? Well, you always have the origin in play here. So our position vector for A as a column vector, -275, our position vector for B, 4, -3, 2. What we could do if I wanted to go from A to B is I could go from A back to the origin, and then from the origin go to B, which is the same as B minus A. And if you went 6 in the x direction, then down 10 in the y direction, and then down 3, you will go from A to B. The mathematics is a lot easier than actually drawing it out to see what's happening. Which is, again, somewhat of the power of math, right? You could figure out how to get from that point to that point, working in 3 dimensions and figuring out and counting and all sorts of stuff. But dealing with the vectors makes it really, really easy. And then if this is A to B, B to A will just be the negative of A to B. So the same vector in the opposite direction is just the negative. That was one of our properties. So the idea with adding vectors, you can add vectors together if you add a tail of an arrowhead to a head at the same point. So we see that here that Q goes to P, and then you go from P to R. You started at Q, you ended at R, so we could call that the vector Q to R. Vectors aren't worried about how you got there. They're just like, you started here, you ended there, that's where you went. You went along that vector. So as long as those middle things are the same, and you're attaching the head of one arrowhead to the tail of the other one, that gets you your resulting vector. And you can move things around as well. So Q to R, this makes sense, going from Q to P, and then P to R. Now, what have I done here? I have this is not as intuitive looking. Okay? It's saying that if I wanted to go from Q to R, I could go from P to R. So I'm going to draw that out here. Here's where I'm starting. I want to go from Q and I want to end at R. Here's where I want to end. Start at the green dot, end at the blue dot. The first one's obvious and saying I could go from Q to P. That makes sense. I can see it on my diagram here. That would end here. And then I go from P to R. Did I start at the green dot and end at the blue dot? Absolutely. But the second equation there says I first want to go from P to R. So I'm going to take that vector, I'm going to draw it in purple here. This is P to R. And I'm going to drag it up here and say, okay, if I start from Q and I go from P to R, I'm way up there in space. Not sure where that is. And then I want to subtract P to Q. Well, P to Q is normally this one in orange. But if I subtracted, it would go in the opposite direction. And if I drag that
and put that tail to that head.
I end at R perfectly. Just kind of cool that I can drag things and it works out that nicely. It's much easier to visualize it using the arrowheads that were there and the lines that were there. Moving it off into space is a little bit more confusing. In these two equations, can you see that both of them have P to R? And then here, Q to P is equal to negative P to Q. So I just did that substitution. Two different ways from get from Q to R. So we've got the vector xy in 3 dimensions and xz in 2 dimensions. In 3 dimensions, sorry. But it would be 2 dimensions because there's a 0 there. But it's in 3 dimensions as well. And we want to find the vectors from y to z and z to y. You can make a theoretical 3-dimensional picture. It's not drawn to scale, obviously. Drawing it to scale, we did the last one, drawing it to scale. They take time and they're kind of annoying. So just randomly pick a point y and say, I know I can go from x to y. And I know that I can go from x to z. And if I want to start at y and end at z, so start at the blue dot, end at the green dot, I think this is very visually easy to see. I could go from what? If these are the only pathways that I know, I could go from y to x, and I could go from x to z. We do this all the time without even thinking about it. You need to go from one place to another place. There's a river in between. So the direct path doesn't make sense. So what do? You follow the road until you get to another road, then you go across the bridge, and then you go on the other road and you get to where you want to go. The direct path wasn't possible. But in the end, you started at the blue dot, you ended at the green dot. So starting at the blue dot, and if you've drawn the diagram here, can you see, oh, it makes sense to go from y to x, and then from x to z. Do I have these? Yes, I have x to z, but I don't have y to x, but x to y is just the negative. Add the corresponding components. So adding vectors, really easy. Add the x coordinates, add the y coordinates, add the z coordinates. And since we found y to z, z to y is just the negative. And I put here, you could use this formula. And some people like memorizing the formula that y to z is just z minus y. But I find drawing the picture and seeing the pathways very intuitive, and it makes sense. Using the formula, especially if you're using the z minus y, you can't see it as nicely on the pathways. So the position vectors of 3 points A, B, and C are given. This is in 3 dimensions. And we want to show that they are collinear, meaning all 3 of those are in a straight line. Now, if we take this back a step and you had the same question in 2 dimensions and you had 3 points, what are some of the ways you would find it in 2 dimensions that they're in a straight line? I mean, graphing them, I can see that they look pretty straight right now. Yes.
Check to see if the slope of A to B is multiple of the slope of B to C.
So I could check this slope, and I could check that slope. If those slopes are the same or are like in 2 dimensions, the slopes we just always reduce, right?
Yeah.
So in 2 dimensions, if we say if those slopes are the same, then obviously they have to be in a straight line because they share a point, right? If you had 4 points and had 2 slopes that were the same, they might not be in a straight line because they're not sharing. You'd have to check the slopes between each section. If all those sections had the same slope, then they would be in a straight line. Okay, great. You could use the slopes. Another way that you could, in 2 dimensions, figure out that those are in a straight line. If I figured out how far that was and how far that was, and it happened to be exactly the same as how far that was, they would have to be in a straight line. If they weren't in a straight line, then the black line would be slightly shorter. So we could use distances. So distance or slopes, this is what we want to show, that these 3 are in a straight line. B to A to B is that direction vector. B to C is that direction vector. Do they have the same slopes? Are they multiples of each other? If we multiply AB by 3, we definitely would get BC. So since they're parallel and they share the same point, they must lie on the same line. But you could also figure this out with distances, but then you would have to figure out, remember the notation, this is the distance from A to B, and the distance from B to C would have to equal the distance from A to C. So the distance method is definitely more work. Because in the parallel method, you just needed to find vectors AB and BC. In the distance method, you'd also have to figure out vector A to C. And then you would have to do, remember how to find the length of a 3-dimensional vector? It's just A squared plus B squared plus C squared in the square root sign. So for example, if I wanted to figure out the length from A to B, I could just add those up. So 2 different ways. Definitely the slopes way is quicker and makes more sense to do because it's quicker, but the distance way would also work. Okay. I want you to try question number 5 on your own. put up the answer in a bit. All right, did you find vector a to b to be -1, -4, 10? And then its length, the distance between those 2 points, a squared plus b squared equals c squared, the square root of 117. So we've already alluded to this, but now we're going to formally talk about adding and subtracting vectors. So there we have two vectors, the vector u and the vector v. When we talk about adding vectors, u plus v, this means you first move along the u direction, and then you move along the direction of the vector v. And the result is, if I first did this, and then I did this, it would be like, there's my starting point, there's my ending point. That's just what happened. So we call that the resultant vector. We started at u, we went to v. We always attach the head of one vector to the tail of the other vector. So this, my purple vector's tail is there, my green vector's head is there. And the resultant vector is u plus v, because we started at this point, started at this red point, ended at this orange point. The order doesn't matter. You know how we went through the properties of matrices and we found out some weird matrix properties like multiplication, the order matters? Adding didn't matter for matrices. Adding doesn't matter for vectors. U plus v is the same as v plus u. And in this one, we've gone 9 to the right and 5 up. Now, if we look back at what v was and what u was, v was 4 comma 5. So I'm going to write this as a column vector. 4 comma 5. And u was 5 comma 0. So I'm going to write that as a column vector. 5 comma 0. And the answer becomes 9 comma 5. We've already seen this a little bit before, but adding vectors is super easy. You're just adding the components. 4 plus 5 is 9. 5 plus 0 is 5. Life is easy and straightforward that one. So if we add the corresponding components together, especially if we look at column vectors, it's really easy to see them now. So same vectors, if we were subtracting, if you had u minus v, and again, the math is really easy. If I look at the corresponding vectors, I could just subtract components. It's perfectly fine. Visually, what's happening is first you're going in the direction of u, and then you do the opposite of the vector v. So the negative sign or subtraction is still adding vectors because you're still attaching tail to the head of a vector and getting a resultant vector. But when we're subtracting, we're just going in the opposite direction. If a is 2i minus j, in other words, a, I'll write it underneath here, call probably got it underneath one of these boxes anyways. Again, life is easier if you look at column vectors. And my vector B, -1, 3. Can we draw A plus B? So you draw your vector A, you draw your vector B, and then the resultant, A plus B, would be as follows. B minus A. Now we draw our vector B, we draw our vector A in the opposite direction, and we get B minus A. Draw two B's, draw two A's, and you would get 2B plus 2A. So if you're, once you've got these written down, if you want to turn the page, try the next couple on your own. Check how you did. Try this one on your own. I like drawing a picture. So I'm starting here at A. I want to end here at C. I can do that by going from A to B and then B to C. Drawing the picture makes it really obvious that A to C will be A to B plus B to C. This is also really obvious because here when we're adding things up, those things match up. So you just write your vectors down, add the corresponding components. And we'll just do the example at the bottom. Well, we got two more actually. You can see if you did this one. Again, I would draw A to B and A to C. If I want to find B to C, it makes sense that I go from B back to A and then go from A to C. So B to C will be B back to A and then A to C, but I don't have BA. Instead I have AB, but B to A is just negative of A to B. This just says B minus A, but you don't need to have that, it's fine. And finally, the last thing we're looking at today is the zero vector. The zero vector basically means you don't move in any direction. So if you went from P to Q, and then went from Q to R, and then went from R to B, then you've gotten right back to where you started with. This is Paul. He's going to his friend's Quentin's house for a bit. Then he's going to his friend's Ryan's house for a bit. Then he's going back home. And at the end of the day, he's back where he started from. So that would be the zero vector. The zero vector is why I'm not very motivated to be a runner. Because I could leave my front door, run around the block, and get back to my front door. And when I get back there, I was like, it sure would have been a lot quicker if I hadn't gone for a run. I could have got back to the same spot right away. I guess it's good to exercise, but that part, if I'm thinking in vectors, I'm just back to where I started from. So that is your zero vector. So that's where we'll end for today.